Okay, so yeah, this last lecture here will be about 5G new radio, which is the physical layer of fifth generation. Again, it's a very advanced and modern topic. It's difficult to be found summarized appropriately in internet, and I rely on this very good presentation of the head of radio interface group of Nokia. Yeah, this is actually for both MOB and MOC. Okay, so I'm saying that because I got a couple of mails from you saying that this lecture will be about project only or for MOC only. So there was a misinterpretation of my words where I said something that is not clear to you. So I will repeat that during the review lecture, but I probably circulate also a message to be crystal clear. This is recorded and yeah, hopefully each and every person will be actually listening to that. So, yeah, essentially, as I said, there are 38 slides here. Okay, so I don't need you to remember each and every detail in this presentation. I will point you to the important parts that are also assessed here in this exam. So the first part will be on new radio. The second part will be actually in related to the project. Okay, 10 slides where I describe the project. Okay, so yeah, keep an eye on the recording program, because apparently this morning has done something wrong, and the information here are really important. So let's start with that. So all of this is about the fifth generation, as I said. So essentially, yeah, first of all, you ask yourself, what are the key features of fifth generation here? Okay, as we transition from 4G to 5G. In here. So here is a nice summary on that. Again, it can be summarized in a few words, essentially. For me, there are three main features, essentially. One is 04, okay, or given that, given the first one, there are three main features for me. The first one is that the spectrum is extremely flexible, extremely broad. Essentially, so you have sub 6 gigahertz bandwidth there, but you also you jump all the way to millimeter waves beyond 28 gigahertz essentially. Then what you have also massive MIMO and beamforming. So 5G is extremely based on beamforming. Yeah, link carrier for low energy, low power consumption and less interference. A very flexible frame structure, as you will see later. Scalable in sense that the OFDM symbols are fixed number, but they have different sub-carrier spacing. So that's the flexibility we meant here. So this is called typically scalable numerology. You have different numbers concerning time and frequency coming into play. Yeah. So then you have aggregation, something we've met already in 4G, LTE. This can be actually done in an heterogeneous way between 4G and 5G, or LTE and 5G, in a sense. And yeah, beamform control, that's necessary essentially to have a broader coverage. Okay, especially at millimeter waves where you have a very limited reach because of the absorption of the air, essentially. Okay, so yeah, bandwidth, there was an option during the last Radio Access Network conference there where telecom operators bought different bandwidths for different countries. The bandwidths are around those three main frequencies. So you have a first low frequency here, 600 megahertz, 700 megahertz here. Then you have 3.5 roughly gigahertz, for China and Japan also 4.5. Then you have 28 and 39 gigahertz. Those seem to be really the two golden frequencies for millimeter waves that have been selected. And then you have other complementary bandwidths. Yeah, important ones are actually those beyond 30 gigahertz, 40 gigahertz, and 50 and 70. In particular, will be for beyond 5G. As you increase the frequency, you appreciate that the cell needs to shrink, because the reach is limited, so you go all the way from macro cell to small and ultra small cells when you get to proper millimeter wave range. Okay, we'll see also that when you have less than 1 gigahertz, you can actually cover an entire cell quite, quite easily. When you go down in frequency, what you can do, you could actually think of staying in a macro cell and covering limited sectors inside the cell. We see that this is actually a feature that is extremely useful in 5G as well. So we start to sort of enter this concept of beamforming control, which is really the heart of 5G technologies. Okay, so in particular, all the bandwidths have their purpose, essentially. Not all the frequencies are used for every application. Actually, 5G is extremely based on what is the particular use case that you handle. It is Internet of Things, whether you get into manufacturing processes and you want to control robots, for example, whether you're in indoor environments or whether you do, I don't know, e-health application in hospitals. And those are actually defining requirements in terms of link packet loss rate and delays, etc., that can be measured in order to grant a certain quality of service. So it needs to be extremely flexible. For 5G, of course, the reach is limited, which is indicated by this, essentially, this sort of oblate spheroid here, which is short, but the capacity can be augmented dramatically. Here, 20 gigabit per second is what you can get to with bandwidth of essentially 1 gigahertz in here. So it's really gigabit type network. For LTE and MIMO at lower frequency, you can again increase the capacity by a factor of 10 probably, not huge, but you can actually increase the capacity bringing in massive MIMO, for example, which is more effective. And bandwidths are actually 100 megahertz, so a factor of 10 less than the 5G millimeter waves, leading to 2 gigabit per second. LTE done at 700 and 800 megahertz here. It's actually, that's actually the important information. That can be, for example, for IoT and critical communication here. Now, being the frequencies low, they have a wider coverage. So you don't really look into the speed, but you look at the stability of the link. Okay, in critical application, I mentioned e-health in hospitals, for example. You need a stable connection there for vital signs monitoring and stuff like that. Okay, so the coverage needs to be broad. The data rate is not necessarily high, actually it's low, because you send few data, sensor sends sort of small packets, if you think about that, right? Just, reads a temperature, reads a particular physical parameter, etc. So you don't need a huge bandwidth here. It's good to keep it down, but the coverage needs to be extremely large, needs to be extended. Okay. So, we can say here you have a limited coverage and high capacity, here you have low capacity and large coverage. So there are two complementary situations as you swap from sort of microwaves to millimeter waves if you want. The spectral efficiency is another feature of that. What is the main point here? We learned in LTE that we can aggregate 5 bandwidths of 20 megahertz, getting to 100 megahertz bandwidth. It's possible with that technology only having a certain gap between the bandwidths, so it's not really 20, it's actually 18, to leave these guard bandwidths in order to assure the control switching that goes the right way. While in 5G, actually what we have in here is that we can cope, since we have extremely high bandwidth, you can cope with something that is actually already broad, getting to 100 megahertz without aggregating small sub-bandwidths. So that's what you can do, essentially. So this seems to be trivial, but it's not, because, doing something like that, you remove all the extra information or the extra processing you need to discriminate between sub-bandwidths. So it's actually lighter in terms of processing in here. Okay, so faster load balancing, less common channel overhead, less overhead, faster balancing. And of course, you waste in LTE 10% for this guard bandwidth. Here you see, you have just 98 megahertz, so you waste just 2 megahertz in here. Here you actually waste 2 times 5, which is 10 megahertz, unfortunately. For guard bandwidth. Okay, so in this sense, 5G is spectrally efficient. And also synchronization is the same sort of paradigm. In frequency, you remove guard bandwidth. In time, you remove synchronization symbols. So typically in 4G LTE, you send off a synchronization symbol or a bunch of synchronization symbols every 10 milliseconds to assure, again, from empirical studies, it's been demonstrated that this is necessary to keep up the link, in a sense, and synchronism within the link. In 5G, technologies will push this to 20 milliseconds. So it's actually, there's no need of a regular synchronization symbol every 10 or 5 milliseconds in there. It's actually a bit more relaxed in terms of synchronization. So, yeah, why is that? Because of the essentially the better time basis and synchronization mechanisms that are implemented in 5G. Yeah, we didn't go through all these sort of synchronization symbols in 4G, so I don't pretend you remember those, but there are different ones. There are primary, secondary. Typically, the broadcast is the one that is actually given the synchronism across the frames in there. So, as you can see, is sent off every 10 milliseconds, but there are intermediate ones which you don't need to remember. Okay, so it's more relaxed in terms of synchrony, so try to look at that in a broader way. Okay, we're not entering the deep detail here, we're just grasping, where are we going, what is different, what are we changing with respect to 4G. Okay, you have all the basis from all the previous 10 lectures that I've made. Essentially, here we look forward, and there are still sort of paradigms or properties that are difficult or hard to achieve with current technology. So that's where we want to go anyway. Okay, so for example, yes, slide 7 is not important. You don't need to remember all these physical channels, but just remember the physical layer as a structure, of course, and there are different logical channels within the frame. And yeah, the synchronization and the communication happens between any user equipment to the base station. There is called G node B, GNB, okay, in 5G. But don't remember those, okay? Don't remember those by memory, all these acronyms. This is actually more important in here. Yeah, that's what I was talking about, what is probably related to what we know better from previous lectures. Okay, so we know that we can fit in a certain subbandwidth for OFDM. Okay, inside the essentially the frame, as we'll see later, in frequency. Okay, so every subcarrier is spaced with the next one of a certain bandwidth. Typically in 4G, this is rigid, was 15 kilohertz. Right, in 5G, this becomes really flexible. You have the infrastructure to actually expand that from 15 kilohertz all the way down to 120 kilohertz. Okay, so the frame structure is prepared to absorb scalable numerology in here, starting from a bandwidth of 10-20 megahertz from here, passing to 100 megahertz for smaller cells, essentially. Right? Now to indoor, for example, you have 200 megahertz because it's carried in space more, of course, and you have actually up to 400 megahertz, which is the maximum total bandwidth covered by 5G in terms of millimeter waves. Okay? So this is actually, this point here is extremely important, that you have flexible subcarrier spacing, SCS, here, okay, that defines a very flexible numerology. Why those numbers? Because they're actually well suited for doing FFT processing. Okay, they have powers of 2, essentially. Okay, this is extremely important to remember. Slide 8. Slide 9, again, I don't want you to remember these, okay? You can tell for yourself what makes sense and what is not. Okay? That doesn't make sense to remember something like that. It's just, I use that as an excuse to sort of complement the discussion on numerology and sort of relate back to this thing that I said at the beginning, that 5G is really related to the use case that you have. You may ask yourself, what does it mean really in terms of network infrastructure? We have a concrete element in here. Okay, we've been seeing the frequency division in the previous slide. and how it is organized. Now, in the time domain, there is actually a structure that borrows the meaning of the use case that you're going to tackle in particular. And that's a real novelty here. For example, you have these fields, v2x, embb, urllc, and then you have emtc, iot in here. What are those? You know, really confusing, I guess, if you see that for the first time. Okay, what does it mean? Well, it means that the frame itself is structured to absorb certain types of data. For example, EMBB is extending mobile broadband. It's pure metropolitan communication, pure urban communication, really mobile in its context. Okay, so any application that requires a broadband, you watching a movie, for example, or listen to the music or doing anything else, will go into this broadband structure. But there are other fields, of course, that have a different purpose. For example, vehicle to infrastructure. Okay, you may need to communicate with a vehicle that goes at high speed, and for which the Doppler shift is more pronounced. Okay, so you need an extra field to tackle that. Okay, you know that this is basically subject to different physical requirements. Okay, so you need to rework the numerology for that in both time and frequency. Okay, but you know that you have a dedicated field to communicate with that. You don't need to readapt the entire network structure. It's already prepared to do that for you. Same for broadcast, and that's something that reaches everybody independently on numerology, essentially. Then you have the interesting ones, the Internet of Things. Okay, that's actually essentially the Internet of the future, where all the objects are connected together, domotics and lamps and other bulbs, etc. All these things that are not sending millions of data. They're sending few data, but they need essentially a continuous connection and a reliable connection, right? And massive machine type communications, and that for example, for the smart manufacturing environment, there where you have lots of machines connected together, there where you need very low packet loss rate, because you can't afford blocking an entire production line. Okay, so it needs to be crazy reliable in there. And again, they deserve to be treated separately there. In general, there are these URLLC, that means essentially ultra reliable, low latency channels. Okay, they are reliable and low latency whenever you need very low delay from end-to-end link. Essentially, you need to use those fields in there. Okay, so those are again for mission critical type applications. Yeah, you don't need to remember all of these, but just to sort of try to, grasp the philosophy for which 5G is developed in here. Okay, yeah, this is another important slide, slide 10. Okay, I'll start to take notes now that I will post a Moodle for you to facilitate this. So essentially what we have here is again a scalable numerology for a new radio here. You see again the sub-carrier spacing sort of stretching from 15 kilohertz down to 120 kilohertz. The message here is that, as in 4G LTE, you remember we had 7 OFDM symbols there, right? Here we actually doubled the number of symbols here. We have 14 OFDM symbols with different numerology. So if you fit, of course, 14 symbols with 15 kilohertz, and then that takes essentially in time, it takes more time. Okay, well, if you fit actually 14 sort of OFDM symbol for 120 kilohertz, this actually shrink in time. So the message here is that the slot duration is always commensurate with 14 symbols. So whatever they are in terms of duration, they fit 14 symbols. Okay. So slot, the fundamental time unit, which is a slot, is made of 14 symbols, but with different numerology. So with different timings. Okay. Yeah, you have to be really precise. You have 1 millisecond for 15 kilohertz, and you have 0.125 millisecond for 120 kilohertz. Okay. So duration is different as you change the sub-carrier spacing. Okay, but all designed to fit 14 symbols. And of course, you can aggregate different slots for numerology. Okay, yeah, there's no need to remember that. We get to 12 all the way in here, where there is another important feature that I'd like to point out here. Don't look at the sort of handshaking procedure to establish a connection here. What is important here is just that the base station, what we call G node B in 5G, is actually able to discriminate beams. Okay, so to really do beam steering. And there is a specific field in the frame that does that, which is called SS block. Okay, it can go from 1 to n, and it's already prescribed to reconfigure the antennas in order to point towards precise directions. So that's extremely important. Let me start to write down in the notebook here what is important. Let's check on the recording. Okay, seems that it goes well. Right, so this is going to be essentially an introduction to 5G and R, which is the physical layer of 5G. Okay, indicated with capital letters PHI, Y typically in the literature. Okay, so as to avoid creating confusion, we started, let's see here. Important slide is slide 2. To 6. Those are important slides. Okay, I'm gonna write them down in this column here. So it's slides 2 to 6. Okay, those are essentially about the key features, right, of 5G. Okay, what are those key features? Essentially, we know that there are roughly 3 bandwidths. One is low frequency, 700 megahertz. Then we get to 3.5 gigahertz, and we get then to 28, 39 gigahertz in here. Okay, for millimeter waves, essentially. But the three key properties, I would say, of 5G are definitely summarized in this way, which I like. So we have essentially high spectral usage, and low power, lean carrier design. Of course, both at sub 6 gigahertz, so I'm referring to 700 and 3.5, and millimeter waves. Second feature in here is massive MIMO and beamforming, which will we have seen that already, but we'll see that we saw massive MIMO, MIMO already. We'll see massive MIMO a bit better later on. Okay. Massive MIMO and beamforming. Here. We've extended coverage. So there is a backhaul network that orchestrates all of these to extend coverage. Third characteristics in here is definitely what we like more, which is the scalable numerology joined with OFDM. And also, this is actually another thing that I like, essentially aggregation, hybrid with LTE plus 5G. Okay, sorry, is there any question? Sorry, my writing is probably not brilliant here. Sorry about that. Yeah.
High spectral, what comes after that?
Oh, yeah, sorry, okay. Apologies. Okay. Let me write it better. I spectral is readable, right? I spectral usage.
Okay. What's after that? That's second.
Sorry?
After usage.
And lean carrier design of sub 6 gigahertz and millimeter waves. These things, sorry, the surface, you have to write extremely slow. For my hand at least, to get it everything.
That's 64 gig.
That's that's 6 gigahertz. Sorry, let me write it down. 6 gigahertz and millimeter waves. I'm repeating the information that are in the slides anyway in a summarized fashion. So yeah. Okay. Just send me a mail or drop by if you don't read those notes. I appreciate that. Okay, but I repeat, it's recorded, right? It's high spectral usage and lean carrier design at sub 6 gigahertz and millimeter waves. That's point 1. Point 2 is massive MIMO and beamforming with extended coverage. Okay. Point 3 is OFDM with scalable numerology plus aggregation with LTE plus 5G. And that's what we've seen so far. There are other properties, of course, that essentially are related to base station densification, for example, which I put on the other side in here. Okay, since essentially the range is limited, right, of 5G, so you have to be prepared to have many more base stations as you increase the frequency. Or the counterpart of that is that cells are shrinking down from macro to small to ultra small cells. So this leads to base station. Just to give you the perspective, in the territory you'll have a densification which is much higher. Okay. So I would say here's an extra feature is high base station densification in here. Okay, so reduction of cell size. Okay. Yeah, target data rate is essentially 10 gigabit per second. Okay. As if you're asked, okay, you followed mobile communication module, can you tell me what is the special property in terms of data rate of 5G? If some of your friends or your parents, etc., ask you that, they say, well, we aim at arriving at 10 gigabits per second, which is not possible at the moment. Okay. So the local capacity is also enhanced. Local capacity is essentially enhanced. Sorry, yeah, it's actually multiplied by a factor of 1,000. Yeah, so to speak. Okay, so slides 2 to 6 for the moment. If I don't write the slides here, you don't need to remember. You can read for your own understanding, etc., but you don't need to remember certainly things that are, for example, in slide 7, if we go back there, we remember that, yeah, you have loads of logical channels. There's no point of remembering that. Slide 8 is actually important. Yeah, we touched on that a little bit already, right? So it's actually within the scalable numerology. So here I can be specific actually, and I say this is slide 8 actually, related to the feature 3. Not only, because as we remember, we have also an implication in time and the logical division. So also slide 9 and 10 are related to the scalable numerology that we saw. Definitely we're not interested in that, 11, but we're interested in 12 more. So here actually I would say slides 8, 9 and 10 are important and are actually related to this point 3 that I summarized here. Okay. Yeah. We try to sort of sort out what are these million promises of 5G. Okay, if you start to dive through the literature, it's really confusing. So that I think this lecture has the purpose of sort of trying to guide you towards the main features, but it's quite convoluted, unfortunately. Yeah, so we need to unfold and understand a bit better this one. Okay, so yeah, essentially slide 9 is important, and we touched on that. And yeah, essentially also remembering if you want the timing, that you have 1 millisecond sort of at 15 kilohertz of subcarrier spacing, and you have 0.125 milliseconds if you have 120 kilohertz as subcarrier spacing. Okay, so let me do something like that for you to discriminate across the various chapter. Okay, so we are now down to slide 12 here. Yeah, we'll see whether we'll expand that. Slide 12 is important because you have these beamforming frames, these beamforming fields that are actually called SS blocks. Okay, so beamforming what are called SS block. And that actually determines the direction of propagation here. Okay, this is the key slide, I would say, okay, for this thing. Let me write it down. Slide 13 is extremely important for me because it relates back to what you learned about the structure of 4G, in a sense. Here we see really the frame structure. Okay, so this is important. Yeah, let me discuss that a little bit. Okay, we saw essentially the slot, and inside the slot, what you have is essentially this field that is called SS. Okay, so a sub-slot in a sense. Okay. A sub-slot has duration essentially of 5 milliseconds, as you see in the top left slide. So this is typically called a unit or a burst. And this sub-slot has very rich structure in here, but it's not shocking to know or to see that essentially it will fit all the subcarrier spacing numerologies that we define. And so you have actually a field for the 15 kilohertz, a field for the 30 kilohertz, a field for the 120, and for 240 as well. That is another numerology. Okay, so in these 5 milliseconds, okay, you have with different frequencies structure that is actually fitting all the OFDM symbols in here. And within these slots, actually, you don't only have OFDM symbols, but you actually have essentially what are called the SS blocks. Okay, so what I defined in the previous slide. Okay, so the question would be, turning things around, you know, these SS blocks, we know what they are, we know what they do, they define the direction of radiation, but where are they inserted, or where can I find them inside the slot? Okay, so the slot is, the answer is, the slot is subdivided into subslots, SS, okay, and the bars encodes all the numerologies, okay, from 15 to 230 kilohertz, duration of 5 milliseconds. Inside every unit in here, you can find different SS blocks. And as you can see, each SS block, you know, depending on where you're going to activate, where you're going to put bits at one, so to speak, you know, you can actually determine how to steer the beam. Okay, for each and every numerology and each and every SS bars. Okay, so I need to send a certain data. The data is fragmented into bars, so to speak, you know, structured according to the modulation the data has. Where do I send, in which direction, to which user? I can decide that through the SS blocks. Okay? If you think about that, it's extremely powerful. Okay, the first time that we see such a complicated structure in telecommunication. Okay, then each and every SS block has, of course, data, and you have subcarrier number, and you have essentially all these control channels defined. Here you don't need to remember the detail of an SS block. I want you to remember what is the mechanism to actually beam steer your information. That is up to here. Okay, is the key image, and now it fits inside the SS burst. Is the important information. Okay, so I would say essentially remember where SS blocks are, which is SS burst. Yeah, the SS burst itself actually fits or fitting different numerologies. Okay, for subcarrier spacing. Right, so yeah, I suggest you to remember that, because you sort of close the loop, right? And you know what a slot is, and you know how it is organized. The sub-blocks are 5 millisecond length, or 5 millisecond length, and yeah, essentially you have SS burst 5 millisecond long. Okay, they are organized so that essentially every row fits a numerology, 15 kilohertz all the way up to 240 kilohertz here. Then they are divided according to the timing. You know that it's 1 millisecond for 15 kilohertz. For 15 kilohertz, for example, for 120 will be 125 millisecond, which is actually defining, as you can see, a finer division in here, right? And then every block, essentially, inside these will have a series of SS blocks in here. Okay, so this is an SS block. Okay, and that actually defines where my antenna will radiate the beam. This is basically, let me bring it up. This is basically what you need to remember. Okay, you have an SS burst of 5 milliseconds. Yeah, then you have a number of essentially slots that are defined by the numerologies. If it is 15 kilohertz, is 1 millisecond. If it is 120 kilohertz, is 0.25 millisecond. And each and every block here has each and every slot inside the burst has these SS blocks that define the radiation angle. Yes?
So it's just a field.
It is a field, yes. It is a field. It is a field, but you have to, again, the timing, the frequency and timing helps you to encapsulate the information. Once you have modulated that, you have to divide into blocks. How do you do that? The philosophy is always to do that in a clever way, okay, to fit a certain frame, and then you base all of these essentially synchronism and all the other things that are necessary based on this numerology that you decide in here. Okay? Yeah.
What is this burst?
This one?
No. Can structure remember where SS blocks are again? SS burst.
Yes. Fitting, okay. So the SS burst will fit actually the different numerology. It's explained then here. So it's this one and the other slide. Okay, different numerologies are defining different subslots there. So which fits different numerology SES. Okay. Good. Yeah, no need to remember slide 14. Actually, slide 15 is another important one. You can tell for yourself why. Because it's actually dealing with massive MIMO. Massive MIMO is extremely important in here. It is an extension in the sense that you use more and more elements, more than 8 in here, and it can be adapted by tuning gain and phase of the input signal within each and every antenna element. So that's the mechanism to actually achieve the beam steering. Okay, so where, this SS block tell the antenna, all right, you need to radiate in this direction, but actually it's not like that. It needs to tell more. It needs to tell actually the value of the gain and the phase for each and every element in the antenna array. So if I want a direction, this will correspond to a set of amplitudes and gains for the antenna. And then I can realize the beam steering. Of course, being multi-element is not only the sort of the clean beam that we saw in massive MIMO, essentially, but it's also enhancing the capacity in terms of multiplexing. That's really important because we saw what is the mathematical basis there, okay, which is SVD. Yeah. Remember in the chapter where we did equalization and multiplexing and diversity. Okay. Massive MIMO enters the 3GPP standard, actually for 5G, already in actually release 13 here. Okay. With 16 elements and 32, and then we actually in release 15 and over, now we're at release 16, you actually think of more than 100 elements for the future. Okay, so slide 15, 16 and 17, those are essentially the requirements for which massive MIMO is important. Capacity, you can obviously, we think that we will run out of capacity by 2020 in spectrum less than 3 gigahertz. Is extremely crowded. And that's a reason to go sub 6 gigahertz and then also all the way to millimeter waves. Okay, that's a motivation. Okay, but we know that below 6 gigahertz you have essentially low carrier frequency that can reach larger areas, and above 6 gigahertz you have large bandwidth, but actually the path loss is poor and you reach a limited space essentially. Okay. So this is important really. As I said, 3GPP new radio for 5G is extremely beam-based. It's a beam-based air interface. It relies on the ability of steering the beam towards users. Okay, and you see that there was an idea around before 5G, but now has been really concretized in this frame structure that I showed you. And around dedicated fields that actually do or deliver that in the air interface in here. Okay, more than 6 gigahertz. It's a very nice table here that actually summarizes everything. Poor path loss condition is important here. Number of antenna help to overcome a poor path loss because you can increase the gain dramatically. Okay, so even though millimeter waves are really harsh in terms of loss, you can increase the number of elements, create a beam that is extremely narrow. We call that pensive beams. Remember when we touched on massive MIMO. Pensive beams have essentially an extremely high gain at a very limited range of direction, tendentially one direction. Okay, so you don't waste energy inside lobes essentially. That has to deliver networks at millimeter waves. Low consumption, of course, and essentially you can use antenna arrays with elements that are not really defined. Okay, you don't care about the quality or the aspect ratio of the single elements. They need to be small because you want compact arrays, and that's the only motivation in here. But essentially they will play together to essentially deliver selective coverage. Okay, and tendentially you can establish and beamform each and every channel. So tendentially, if you imagine this whiteboard here to be an antenna array for massive MIMO, if it is well designed in 5G, we'll be able to target each and every of you. Okay. When you're in need, you communicate with the base station, then it reconfigures to give the information to those of you who are in need of sending or receiving data. okay, in a cyclic and synchronized way, of course. Right? So that's the tendency in the future, okay, to be really dedicated to each and every user. Not sure it will happen really, but it's the idea that is around at the moment. Okay, yeah, again, a bit of terminology here. As I said, G node B is actually what is the base station. User equipment is, again, our equipment, our smartphone, etc. And yeah, of course, one important thing here is that G node B can actually have arbitrary array size. It's not properly true because you want compact base station to be deployed everywhere. Actually, that's the tendency, right? You want to have a base station for every room. That's where 5G wants to go in the future. And so it can't be extremely large, as I said. Something like that, something like this whiteboard here, or that whiteboard is actually not really feasible. Some say that, yeah, actually we can engineer the walls of rooms and the outside walls of buildings in order to put this, to deliver these large arrays. Okay, that's something where I do a little bit of research. You may have seen one of the final year projects about that. But it's an interesting way forward. And again, we have to explore whether it is really feasible. Okay? So if you look outside, you see that wall is made of many bricks in there. You can imagine that every brick has an antenna element embedded in, and then covering all the sort of face of a building. You can actually integrate the MIMO inside the architectural infrastructure. And that's a really futuristic idea. Yeah, a couple of years ago it wasn't around, so we thought just okay, arbitrary array size is acceptable. Okay, in the base station I can afford to put whatever array I want, but in view of densification, that doesn't really make sense. Okay, it makes sense therefore to do a distributed sort of base station type thing. Okay, while at user hand you have essentially you have the need of a more compact antenna array. Okay? So the two main purposes, this is the, beside what I touched on, those are the two main messages here, enhanced capacity and enhanced coverage. Those are always the target for future 5G networks. Okay, so we have here definitely, if we carry on in summarizing here, we have definitely slides 15 to probably we actually include only slide 19 in here, right? This is actually an introduction to massive MIMO. Okay. The coverage by reducing interference and augmented capacity are the two targets in here. Okay, so coverage, controlling beamforming in a very precise way, enhanced capacity, increasing the number of elements. Okay, so we touched on, also various channels in here, so the motivations, etc. Motivations and channels here. Okay, so this is actually, so I've been talking a lot, sometimes touching on concept vaguely, but let's see for beamforming something a bit more refined in here. So I told you that low frequency coverage is extended, something like that. High frequency actually I can be more selective, etc. So beamform control actually means that when you have low frequency, low carrier frequency, you can actually do in an hexagonal cell something like that. You can actually reach out all the points within an hexagonal cell pretty easily. Okay, because the path loss is okay. Okay, allows you to do that. As you increase frequency, however, and you start to bring in the beamforming structure, what you can do thanks to the augmented gain is actually to reach a certain area in full with a good path loss, okay, but not all the areas at once. Okay, you will reach actually only a limited portion of the cell beamforming actually. Okay, by beamforming in here. So if you, the idea is then that if you have users wandering around, then you actually do what is called a beam scanning, and once you find them, then you start to communicate. Okay, you start to link and to log the user in the base station and carry on the communication. Okay. So essentially, yeah. Then you have to manage the beam a little bit. Okay, you can be essentially, you may have repeaters of base station everywhere. Okay, that are actually in visibility with your device. And we need to know what are the beams of which repeater or which base station that is actually logging in the device. Okay, which is in the best position to use that. It may be multiple beams. Okay, then we need to manage all of these, manage the distribution of power, etc. Okay, so yeah, we need flexible channel state information here, acquisition, in order to understand essentially what is the quality of the link that we establish from each and every base station. Okay. Yeah, the beam management is actually very interesting. Beam scanning and beam management. I'd like to touch on that. The way it works, actually, you go from essentially, yeah, you have a repeater, for example, or a base station. Yeah, so you essentially you do a quartz scanning at the beginning. Okay, so with a wide band, with a wide beam width, if you want. Right, so you scan position 1, 2, 3, and 4, example, and then you see that there is somebody in position 3, for example. Right? Then what you do, you discard all the other beams and you carry on with the amplitude and phase for the array antenna here that creates the beam number 3. Okay? Then once you do that, what you do is what is called the beam refinement, essentially. Okay? Beam refinement is to create pencil beams that are narrower within the initial beam that you find. Okay, then you redo sort of a second scan here, and you see that actually the one that intercepts the user better is number 2 within 3. Okay, then once you do that, you do also the same procedure from the user end, which will quartz scan the surrounding environment, and then confirms that there is a beam in 3. It does refinement as well, and then you have essentially 2 pencil beams that are perfectly aligned between base station and user end. Okay, so you see it's a terribly complicated procedure to do. It's easy to say. Imagine what's going on in rephasing and doing this time. Imagine to do that for each and every user. Okay, so there is a need of a very sort of deep management of the beam in there. But that's where we're heading. Okay, so yeah, I would suggest here to actually focus on 20 and 21, because it's really fascinating, this concept of, so I put it down, slide 20 and 21 here. So this concept of beam scanning and refinement. Yeah, we don't care about the next 2 slides. Of course. Yeah, we get a summary here that may be actually interesting. Yeah, I didn't mention this word code book. Yeah, essentially, imagine to do this refinement, beam scanning and refinement for each and every user. Then you will have to keep track of all the users that you discover for each and every base station. So there is a book, essentially, a table, internal to essentially the backhaul network, okay, in the cloud computing that connects all the base station, if you want, that actually keep tracks of what is the beam in the specific base station that is locked with the essentially with the user, with the specific user. Okay, because from there, find that the refinement is done and the user is found, then the beam tends to chase the user in general. Okay, so you need to sort of have a map establishing correspondence between base station and users, and what is the beam in the base station that leads to that user and this other user. And this is called typically a code book in here. yeah, this is actually interesting. I don't want you to spend too much time reminding that. Actually, yeah, I would really focus more on slide 28 now. And essentially, as an interesting information, okay, if all these technologies that I have in 5G are actually beneficial, okay, this code book anticipated that it means, capturing all the user by scanning a refinement, okay, capturing and locking to the user. Okay, if I apply all of these, okay, so link carrier, new radio, beam scanning, massive MIMO, all the other management for FDM symbols, etc. So, supposed to do this exercise for a frequency that is also used in 4G LTE, 2 gigahertz, for example. Okay, if those technologies are beneficial, then I do expect an improvement already at that frequency. In fact, people has done this exercise at 2 gigahertz here, using exactly the same antenna array, and they found that actually there is an improvement of a factor of 1.5 in using 5G technologies with respect to 4G. So where you get actually with the same bandwidth, same carrier frequency, you get to a data rate that is 7.73 bit per second per hertz rather than 5, and you have for the overall cell throughput, you have 102 megabit per second for 4G LTE and 155 megabit per second for 5G LTE. So it's already, if you apply this to what already exists, is already very good. It's already an advantage. Okay, you don't need to go higher in frequency. Okay, but you need to go higher in frequency because of the spectral crowd. Essentially, you're running out of space below 3 gigahertz, so we need more bandwidth. That's why we're going in a high frequency. Okay, so slide 28 definitely, and slide 30. Now, yeah, slide 30 is not a big deal. It's just I want you to look into that because it gives you parameters that we saw in the second chapter in terms of gain of the antenna, hair of the antenna, in here, yeah, maximum, essentially beam width here, the elements, and yeah, noise figure, for example, yeah, for both the access point and the user hand. Okay, you see concrete elements in terms of air here, the 40 dBm, etc. So just to add the flavor of the numbers that are involved in terms of number of antenna and effective isotropic radiated power, etc. So let me put down slide 28. Okay, I'm just checking it is actually, yeah, so, and slide 30 is just a comparison exercise in a sense, okay? Comparison and antenna parameters. Good. So yeah, the last thing that we can look into is, okay, what are, again, following on this idea of giving numbers, what are the typical size of the array? So we've been talking about small, compact, base station, user end, you may ask yourself, okay, but what is it that physically? Now, how does it look like? Okay, and that's in slide 32 in here, where we have, okay, the first row here is the access point, whatever it is, a repeater, base station, etc. And the second row is user hand. Okay, you can afford more elements in the base station, as I say. 28 gigahertz, typically the target is 256 elements. Patch type antenna here. Each and every element has 2 polarizations, so 2 dipoles that are in a cross configuration, so they can resolve both vertical and horizontal polarization. Okay, so 39 gigahertz is 512 elements, 73 gigahertz, which is in the future. We want to smash 1,000 elements here. Okay, so what are the numerologies here in terms of air and antenna area. You need to keep track of the area covered by these antennas. If here you have say a certain reference area covered by the 28 gigahertz elements, the area say is of 60 dBm, for example. Now, the elements typically here have special characteristics that I want to keep fixed. Let me be more precise on slide 32 then. And this is very interesting. So slide 32, but we actually carry on in the next slides. So I have an array of these cross-polarized elements right here, etc. Suppose you do just a part of this array. Okay. So typically it turns out that you want, in order to create distinguished spatial channels, you want these elements to be statistically independent under rarely fading. Okay? So they shouldn't be coupled to each other. And also these elements should resonate at the carrier frequency. Okay, so eventually what you want is that the side of this patch here is on the order of lambda, whatever frequency you have, right? The order of the wavelength, so that it resonates. Okay? The dipoles resonate. Okay? A second feature here is that you want the spacing between them to be on the order of lambda over 2. Okay? Because it turns out that they are essentially, in a Rayleigh fading, the correlation, spatial correlation goes like a sinc, a cardinal sine function, and the first null after the peak records at lambda over 2, and multiple of lambda over 2. Okay. So this is typically the guideline for designing an antenna array so far. It's very crude. Okay. So it needs to resonate, it needs to be statistically independent, etc. So essentially, those arrays, as I change frequency, I also need to sort of fulfill this requirement to design the array. So if I do that in passing from 28 gigahertz to 39 gigahertz, for example, then the question is, okay, what happens to the total area and to the effective isotropic radiative power here as I get to 512 elements here? Okay, it turns out that as I increase the frequency, of course, I remind you that essentially lambda here is equal to c over f. C is the speed of light in vacuum. F is actually the frequency. So as I increase the frequency, I reduce lambda, so the array becomes more compact in here. Okay, so I reduce definitely the spacing, I reduce the size of the patches. That's actually is represented in these figures, sort of trying to be scaled in the right way. But what happens is that if I pass from 256 elements to 512 here, what I cover is an area which is roughly the same as I increase the frequency. Because of this shrinkage of spacing and dimension. It's actually the 103% of the reference area here. And the area is actually higher, because I increase the frequency, the elements are more, right? So I improve the performance of my antenna in terms of creating pensive beams. If I push this forward, the higher, actually with 1,000 elements at 63 gigahertz, which is a crazy frequency, gets to 72 dBm, and the area covered is roughly half of the area that I use as a reference here. Okay, so that's why it is important to go to high frequency. Okay, improve ARP anyway, make the array compact, which is important. Same is valid, okay, there is more room to grow, of course, but you start to have a crazy number of elements. Imagine to orchestrate all the gain matrix and the rephasing network for these arrays becomes really tangled. Right? But the same is valid for user end, where of course all these things need to go. Imagine inside our smartphone, you left probably an antenna array here at the back, for example. Right? Then this needs to be compact, right? Very compact. So the elements are less. Again, you have a 2-element cell here for 2 polarization, right? I think we have a 4x4 element. Again, reference is this one at 28 gigahertz, 36 dBm for the air, Imagine I go to 39, still 4x4, more compact. The area is the same, but the area is already half of the original area. And if I go to 72, I cover only 15% of the original area, right, with an area which is exactly the same. Again, okay? So it's extremely powerful, again, to go wire frequency. Okay, so yeah, we don't need to remember these. I think you can touch on what are the priorities and ongoing discussions on release 16 here, right, since we touched on the previous releases of FreeGPP. So I would say definitely we touched on slide 32, but you can have a look at essentially slide 35. For 5G, we talk about release 16. Okay, and we can actually conclude. I think you had a lot of new concepts right today to digest. With the very last slide, 38, it shows something remarkable. Probably interest all of our countries here in this cohort. Essentially, there is the United States. Is there anybody from the United States here? No. Anybody from Korea? Oh, good. Japan? No. China? Right. Almost. I'm from Europe. You know. You should be UK also separated from them. Yeah. Sorry?
Same for Nigeria.
Yeah. Right. Okay. Well, how is the deployment there of 5G? Is it ongoing? Probably. No, I mean the pioneering one was essentially 2016 in the United States. You know, they did a lot of work for 28 and 39 gigahertz frequencies. You know, the pioneering experiments of Theodore Rappaport at the University of New York. They did the first 5G link from a building to building in the Brooklyn campus there, and they said they didn't expect that to work actually when they designed the first antenna, etc., in a distance of roughly 100 meters, and then suddenly they got a good signal there with these millimeter waves. Then there is a famous paper reporting on this adventure called something like 5G or communications with millimeter waves. It will work. So it's something that was surprising. They sort of decided to write a paper. Then, yeah, Korea was a pioneering country in 2018 also to take on board these 28 gigahertz and have an experimental network. And then, now, in the meantime, we, through the FreeGPP effort, which is mostly US, EU based, essentially, we actually try to come up with design guidelines and regulations. The three main pillars of 5G are actually mobile broadband, low latency, and high reliability. You remember URLLC, this field inside the frame. Okay, so I want services that are broadband but also low latency and of a certain stability. That's where the massive MIMO can help. Okay, to harden the wireless channel to make it stable. Okay, through a large number of antennas. And then massive machines, massive IoT, so large network complexity is the third pillar. It took basically up to the beginning of this year to define all the regulations for all of us before deployment. Now deployment has started, actually at the beginning of this year, and it is ongoing, probably will finish by 2020, hopefully, and then we think on what's going to happen afterwards. Where we had to having networks that are only based on frequencies that go beyond 24 gigahertz. Okay, so there will be a sort of a transition of the infrastructure from microwaves to millimeter waves, if you want. Okay, but I presume, that's my personal opinion, that there will be a large period of refinement and sort of improvement of the network itself. I don't think everything will work. If you've heard about the Verizon experiment in the United States recently, they said that actually the performances of this first deployment they did, the performances are worse than 4G in their first test. Okay, so they actually need to do better. We all need to do better here. But yeah, we are living now the period of huge rollout on this 5th generation. So it's a golden age for telecommunications, and yeah, I hope, yeah, that's probably a good place to end the module. Leaving you with a probably bright future as telecommunication engineer if you want to embark this profession here. Maybe contributing now to a genuinely new generation of mobile networks. So I hope we haven't had time to get into details of everything, but I believe you have the solid scientific basis to tackle all of these. Okay, especially if you think of reinforcing them through a PhD, or starting maybe a dissertation or PhD. Not necessarily here in Nottingham. We do mostly physical layer here, electromagnetic based computation. There are other places, for example, Sheffield and Imperial College, University College of London. They take care of the higher level of the protocol. Okay, they talk about probably medium access control and applications, etc. Yeah, coding also is another very good area. Protocols in general. You can actually look around, or even beyond the UK, in EU, there are very good groups in there. But it's, yeah, again, I like to think that you learned the basics here, and that will prepare you to sort of embark in a good adventure for the future. All right, so I can conclude here the module, and thank you for your diligence in attending all the lectures. Here I can swap now to essentially the project, which is related to the MOC part of this cohort in here. Okay, briefly, this is the project. Okay, so it will work a substantial percentage of the final mark for those who actually enrolled MOC. It is related to, essentially, it doesn't really include 5G. Yeah, let's make this crystal clear. Okay, it's not about 5G. Okay, in this, it's actually related to designing the coverage of an entire system from scratch, and sort of grasping all the concepts that you learned from the beginning of the module. This is a really valuable exercise for you, really. So I sort of encourage you to do that seriously. Again, courseworks are under marking. I promised you that I'm not going to be picky at all, and that's the same promise I give here for the project. Okay, don't think too much about the mark. Think about putting effort on what you do. Okay, the mark is a secondary thing. Okay, so it's a bit more relaxed in terms of total number of pages. You had 10 for the coursework. I know some of you struggle, but I can't. You have to sort of think of, from my side, if I get documents that are sort of 15, 20 pages rather than 10, it becomes easily difficult in such a busy period to deliver marking to you in the right time. Okay, so it slows down my marking if you give longer documents. That's the problem. And same is valid here, 20 to 25 pages. It means 20 pages. And if it's really necessary, go beyond 20 pages. But it should be strictly 20, 21 pages, 22 including references and cover page. Okay? And all diagrams and data that you find appropriate. This is a very flexible exercise. So you decide how to do that. I give the specification and you decide where to focus again, given what you learned in the module. Again, giving that flexibility has been successful in the past years in getting very high quality papers from you. So I hope it will be the same this year. I'm sure it will be. These are important. In doing this, don't just rely on the material in the slides or on the material in the reference that I suggested. Go beyond that. This is a project. You're supposed to do literature search. You're supposed to broaden your knowledge in order to deliver a project. Imagine you are a telecommunication engineer. Okay, you're taught the specs and you have to deliver a proper design based on your knowledge. Okay, there you don't have slides. If you work for British Telecom, you're sitting in a desk, you have colleagues, so you can interrupt each other. I'm happy for you to do that, of course, although the papers are individual and should be sort of differentiated, but I'm happy for you to interrupt. Okay, but give a bit of personal touch to each and every paper. Okay, plagiarism is still applicable here. I have to remind you, and the university takes that very seriously. So I'm not saying you should work in group and replicate the script. It's an individual work, but you can interact, you can exchange ideas. That's what I'm saying. Okay, you need to pursue different approaches, different routes through internet and through personal reading, but you can interact, of course. Yeah, again, I will post a submission link approaching the deadline or the same day at the deadline. Send me a mail if you get nervous, as you've done for the coursework. Okay, I'll tell you when exactly I will post the link. Yeah, that's the exercise. So you have an island called Virgin Island. Okay, it's remote, it's 1,000 kilometers square, with a major city which is called Media, which is in the north part. And there are 3 areas for this purpose. There's Media City, which is densely populated with an area of 100 kilometers square, and the density of users is 500 users per kilometer square. Then you have a suburban area around Media City, which is 200 kilometers square with a lower density of 100 kilometers square. The rest is essentially a rural area with a very low population density of 5 users per kilometer square. Okay, so for these, you should remind what I told you. You go back to the path loss models, and you can determine the capacity, the set size based on traffic theory, etc. Okay, so you have all the instruments to do that, right? And then we see what the committing agency wants, which is the government. They would like to set up a mobile call. They write a proposal for that, and there are, of course, you will be in competition. So yeah, you should exchange ideas, but imagine you're actually in competition with your friends, with which you exchange information, essentially. Okay? You have 2 networks to design: a voice network based on CDMA, called Division Multiple Access, so 3G data network, to be precise, and a voice network, and a data network based on 4G. Yeah? So you have essentially CDMA and 4G technology. And again, I wrote this down explicitly to avoid a massive number of questions from your side, not because I don't want questions, just because you need to think that you're free, really, to decide. So you're free to propose frequency bandwidth for uplink and downlink within the 4G network, of course. Okay? So, yeah, the final configuration you're looking at is made of a voice network with CDMA again, and essentially a 4G network for data and future data usage. Okay, so what should be the report about? I think you can figure out that. You have to decide bandwidth and frequencies requirement, then you have all the tools to calculate cell capacity, and essentially using the path loss, how you can how you can serve this density of users for each and every area. Okay, so that there is a traffic theory. We've done in the example sheets. You have a good reference also for the exam. How to get to a proper design. Given a certain frequency, a certain density of user to serve, you should come up with a certain cell size. That's essentially the exercise. Then you have to decide the modulation technique for uplink and downlink. Yeah, bearing in mind that you're using CDMA and 4G LTE. Okay, you're already guided by the standards themselves to the users, to the modulation techniques for the users. And error detection and correction methods, okay, again refer to CDMA and 4G LTE. Okay, what's around? That needs more literature search. Okay, to understand. Doesn't mean that you have to design that. It means that you need to find what are the methods that are typically used for CDMA and 4G LTE. You don't have to invent anything. You have to come up with realistic numbers based on what's going on already in the literature. Okay. And then, of course, all of these, as I said, are related. You need to link them all together. The red line is given by CDMA for voice data and 4G LTE. Okay, you've done the coursework on 4G LTE already, on OFDM, in a sense, so you know when I talk about modulation, what's about, and you know the numerologies to speak in the language of 5G, okay, 15 kilohertz for spacing, etc. Okay, so it's actually a very self-contained and I would say also short exercise to be done for the time that you have. But I give you time just because I want you to really go beyond the material in the lecture, to go into the internet, into books and read and discover what's going on and put yourself in the shoe of a telecom designer or a person working at British Telecom designing that. Okay, a network engineer, network planning engineer. Okay. What should you write in there? So, again, all the choices need to be referenced. That's how, when you do a report or a proposal, everything shouldn't come out of the blue. 3 gigahertz, 200 megahertz of bandwidth, randomly. Okay, it needs to be referenced. Yeah, there needs to be a reference to a report or a website or a scientific paper or a book that motivates your choice or your design options. Yeah, you have design options indeed. How do you select across them? You can mention them and you can say, I choose this one, this option, because of this and that. Okay? So, as I said, it's a personal exercise. This is important. You may need personal search about particular parameters that need to be specified. So you have to first of all find out what are the parameters that you need to find, and then do a second literature search for specifying the numbers for those parameters that are realistic and are actually in line with the design exercise. Okay. An example, typical usage time of voice and data service by user, acceptable bit error rate. Okay, I think you have those in mind already. Interference ratios for voice or data, blocking probabilities. Okay, you need, as you apply the things that you learned in the module, you will need data that you don't have. If you don't have this data, you need to come up with numbers, and then you need to go into the internet and do literature search and establish those numbers. Okay, that depends on you. It's your choice, but it needs to be motivated. Okay. You may use, where appropriate, coding, short pieces of code like MATLAB or C to generate data or generate plots. Don't fall into writing a 1,000-line program. Okay, that's not the case here. Right? It's a design exercise. In principle, should be done by hand. But as it gets to some complicated exercise and you want to create essentially plots and graphs, and you should rely on MATLAB, for example. Link budget calculation. Okay, I can actually help you with that, but I do have a code that implements the path loss models and a small code that I can sort of upload, and you may try to use that here, but it's not really it's not really difficult. Actually, you can apply this code, or you can generate this code from scratch, or integrate these or your code to calculation of blocking probabilities or other parameters needed essentially when you're talking about coming up with a cell dimension. You also need to do some market research, of course, on what is essentially the cost or the solution that you're proposing, right? So this shouldn't be a cumbersome section. I'm talking about half a page or 1 page where you sort of try to estimate prices. Yes, and that's also a useful aspect. Unfortunately, remember, you're a competing bid with others, so you need to find those elements. Okay, so there is the choice, there is the motivation of your choice, And then the motivation should actually unfold also the economic aspects a little bit. Not a huge business case, proper business case model. It's just an estimate of figures, if you want, okay, that give you an hope that your bid will be competitive with the others. Okay. Again, in the spirit of putting yourself in the shoe of a British Telecom network planning engineer. Okay. Matter is non-essential. You need to optimize parameter. Graphs may be useful. Okay, link budget calculation available in references. I also posted a chapter of a book that describes essentially how this network coverage is performed. It's a chapter of a book of roughly 46 pages, where you get a very nice overview on what to do when you design, when you do a coverage exercise. Okay, so please read that and try to grasp what are the basics and then embark this this exercise in here. Yeah, I believe, as is the third year that I teach this model, that all the information are there. You sort of confirm that with the coursework. I can tell already that it's very well done from your side. So all the information are there. But if, yeah, as I say, this is actually, it's not about a mark. Okay? You never fail in something like that. Okay, so stay relaxed. Okay? Stay sure that you never fail something. You never get a crazy low mark with that. I'm just talking about you getting at least a very good mark. Okay? At least a very good one. And for this, please accept the idea of doing your own independent research. Okay? Don't limit yourself to the lecture notes. Okay? Just don't limit yourself to what's written in my notes. Just go beyond and do your own literature search. Show me that you actually try to do this proper exercise of coverage, and then I'd appreciate that. Yeah, it's a decision-making exercise, yeah, for something like that. Okay, it's not meant to offend your intelligence, of course. You know very well that there are more than one solution possible for this, but that's the spirit, okay? So don't think there is something wrong, terribly wrong, or something terribly right. You know, there's something that can be motivated, and this is automatically right. Okay, this is the spirit when you do that. Okay, and justifying your own choice, is the true purpose of this exercise. Okay, yeah, right. Okay, those come from previous experiences. Although I never had something like that, actually. That was coming from previous lectures. Okay, it's fine that you want a good mark, you work hard, don't just copy what's around. Just be guided by what's around already, but don't replicate that. Those are the references in here. They say that's a chapter of a book that is actually posted on Moodle already. You may have appreciated that, and then there are other references you may want to start with as you approach this design or this coverage planning exercise. I refer to the reading list also, and basic books for what concerns the application of the essential theories in here. Okay, yeah, for example, CDMA capacity. When I say you have all the instruments, I told you come up with numbers for the signal to interference ratio, etc. It's important. Here, you can see you have bandwidth, you have rate, you have signal to interference ratio. It will lead you to the number of users, okay? You know how many users you need to serve, so you see that there is a straight link to what you're asked and what you need to find your own. Okay? Yeah, in the past I had a few questions about this formula, because as you get into the serious literature, you find several variations of that. Okay, several theories behind CDMA, etc. So use what you prefer. You don't have to stick at the simple version. That's the simplest and the basic version of that. But you may refine one, for example, for WCDMA. Okay, I'm happy for you to use those more advanced formulas, provided you understand each and every element in the formula. Okay, so this actually concludes the lecture of today, and I would say concludes also the lecturing period, so to speak. Yeah, we still have a review lecture. Now focus on going through this exercise, because automatically will bring you to revise all the content. Okay, that's the part. This project will actually guide you gently through revisit each and every concept we touched on in this module here. But we'll do a couple of exercises once we're back in around half May or something like that, in preparation of the exam. Okay, and this is actually for everybody. I record this. I hope people will listen to this recording here. It's valid for both MOB and MOC. It's not only project-based review. Okay, the project part that I've shown is only for MOC, but the review lecture will be for everybody. Yeah, so please attend to your colleagues and friends that they should come over. Although the attendance is still pretty good, I appreciate that. That's pretty nice. Okay, very good, and have a good spring break. Yeah, if there are questions.
Is it possible to post samples for projects?
It is possible, yes, I will do that for you. Okay, it is possible. Again, please use that as a guidance, not as a essentially an element that needs to be replicated and altered in some places. Okay, I will post probably a couple of examples I've done for the coursework. Okay, I take it the coursework was useful, right? Having examples. Okay. Any other question? Okay. Yeah, try to think about that. Now you have this new challenge of the project, so try to do a good job. Yeah.
What did you say the coursework will be out?
Sorry?
What did you say the results for coursework?
Oh, results. Okay, they are undergoing. So we are actually, the target of the faculty is to give everything within the, within actually was 3 weeks after the deadline. So the deadline was the 29th of May. So roughly we're looking into getting you the results by the 20th of April. Okay, so by the end of the week, so the next week actually. My target is actually to finish marking by this week, but it's getting busier and busier, so if you'll excuse me, I may take a couple of days more, but I try to stay within the faculty expectation, because I know that you have then other courseworks to consider with that. Okay? Good, yeah. Yep.
The deadline of this project will be not.
It's posted on Moodle. I forgot what I put down. I can actually. They don't have access to internet, but some of you may check. I forgot what it was. 16. Yeah, it needs to be something around 1 month, roughly. I gave you much more than 1 month. Oh, 12th of May. Okay, 12th of May. So 12th of May, I posted the. Sorry, guys. Yeah, just last thing. I've been asked about the deadline. The deadline is the 12th of May. I posted that project already last week, so 12th is going to be this Friday, actually. So it's more than 1 month for doing that. Okay. I believe it's. I mean, based on the past experiences, and it's enough for you to do that in a serious way. Okay, because there is also the Christmas break in between, and the Easter break in between, so you have a full time to not to dedicate only to these, I guess, but yeah, you will have more time than now, probably. All right, I'll see you in a few weeks, actually, for the review lecture.